Hello everyone, thank you for joining us for the webinar today. My name is Ben Hutchins and I am part of the marketing team here at Innovise. Today we're focusing on the modelling natural flood management with InfoWorks ICM. If you have any questions as we run through the slides today, please type them into the question box located in the right corner of your GoToWebinar interface. We won't mention your full name when reading your questions and our experts will provide answers. Please note that all phone lines are muted during the webinar today. Now let me introduce you to your experts. Firstly, let me introduce you to your expert for the webinar today is Paul Campbell. Paul studied as a mechanical engineer as part of his degree, did a year in the industry working as a water distribution network modeler. He enjoyed it so much he joined the water industry in 2003 as a wastewater network modeler and has been working as a hydraulic modeling consultant ever since. Paul joined the Innovise Solution Engineering team last year, specializing in storm sewer and flood modeling. Joining Paul and your host today is Peter Coombs. Peter is Innovation Manager at Innovise. He is a chartered water and environment manager with 44 years experience. Peter has designed, modelled and delivered a range of storm and foul water networks in the UK before moving to the Middle East for 5 years. For the past 18 years, Peter has been with the Innovise Group, specialising in SUDS, floods, asset management and AI across the EMEA region. So that completes our lineup for you today. Let's start the show. Peter, over to you.
Perfect, and thank you, Ben. Before we crack on, should we just launch the first poll and see who's on the call with us today, Ben? And welcome, everyone. I hope you got better weather than I have. It's been a bit miserable, wet and grey with me today here. So I hope you're in a better situation. So just to see who's on the call, what's the, we've got nature as a major theme today. What's the nature of your organization? Are you from a local authority, a water company, consultant, developer, or other? It's just nice to know who we're engaging with as we go through the presentations today. Just going to keep an eye on the poll and see how many people have voted. Oh, great. We're up 80-odd%. Smashing. Thanks, Ben. If we just share the results for everybody. So we're looking at 55% consultants, 25% local authorities. Interesting. Normally we find we have majority would be consultants around about 60-odd%. So I think we've got a few more proportionally representing the local authorities here today and the water companies, which is great. So thanks for joining us, and without further ado, we'll move into a couple of introductory slides from myself before I hand over to Paul to go through the detailed presentation today. So first of all, for those that are not familiar with natural flood management, what is it? Well, natural flood management is used as a natural process to reduce the risk of flooding and coastal erosion. And today what we're focusing on is the flooding. We don't actually get involved on the coastal side of things too much. So we're really looking at the risk of flooding, and whether that be from pluvial sources, meaning just intense rainfall like we're having today, the ground gets saturated and we get an excessive amount of runoff from the land, or fluvial. So on the left-hand side, I just put in a little bit of background and a link. So if you get the slides afterwards, I've embedded the link to where the Environment Agency are posting information on natural flood management and how they like to incorporate such measures in their schemes. Thanks, Paul. I like this quote from John Curtin at the Environment Agency because he mentioned that the flood resilience is often like working with a mosaic, and even with natural flood management, or NFM, as we'll start referring to it, yet another acronym, sorry folks, but NFM itself is like a mosaic because it comprises of many different pieces. In the photograph here, we're showing a woody debris dam. So this has been sort of put in place on purpose to hold back flows. It kind of leaks with the low flows, and then when you get an extreme rainfall runoff event, then it'll hold back, acting like a dam, and holding back flow right the way up the upper reaches of a catchment, typically. And then we're going to sort of flood the land and the areas that are not going to affect properties, and we've got obviously landowner and riparian right permissions, etc. But I see this as a mosaic, so that's one option. We could plant more trees as another option. We could furrow the land. There's all manner of measures, but natural measures we could use. And I also think about this. I'm really excited about the prospects of using this on a catchment scale. But also, when you look at the micro scale, it's like a SUDS, but on a catchment scale. So with SUDS, we're trying to capture water at source, put in green roofs, permeable paving for the drives, etc., hold back the flows, put in swales with check dams, etc., further up the catchment on a development. We're doing the same thing, but on a river catchment scale, but with natural processes. Thanks, Paul. Where did this sort of emanate from? It's been used for many, many years, but one of the things that really highlighted the need were these devastating floods that happened in July of 2007. And these happened all over the country. We had weather not dissimilar to what we're having this week, in that it rained kind of every day, not too badly, but generally the land just became saturated over the week. And then on the Friday, and I think it was the 21st of July in 2007, we had a rainfall storm cell tracking up from Spain and Portugal. This massive storm cell tracked up the country over Thatcham. And if you see the bottom right-hand corner there, Paul's hit a video play. And this storm cell ran for about 6 hours. I think we had a peak of about 30 millimeters an hour. And the land to the north of Thatcham, so as you look at the diagram there, the top of the diagram is to the north. The land was saturated, and it just ran off and ran through the town. And on the eastern side, you see towards the bottom, there's a large red area. That's the deepest water. And if you look over in the middle there, you can see Piper's Way. That's a detention basin, and that's that big red zone. So it's purposely built to act as a detention basin. But further up the road, we have Kennett School and the lane with Station Road. So the cars being washed away were being washed away about 2:30 in the afternoon, after the schools had contacted the parents at midday to say, look, we got a problem here. The water level was starting to reach the top of the curb at midday. And then by 2:30, when the parents were arriving, they were getting washed down the road, down Station Road. And then the Betteridge Road photograph, this is shown on the Sundays. This is actually a couple of days after the event. And you can see the poor resident, they're still wading knee deep in this flooding to get back to their property. So what happened as a result of these floods, which occurred all over the country, we're just very familiar with Thatcham because that's 20 minutes to the east of Newbury, where our office is, and two of my colleagues who are developers of the micro drainage and the inflow drainage products were flooded with this event. But the consequence was Sir Michael Pitt created a report, a Pitt report and the Pitt Review, which came out in June of 2008. And within it, there were 92 recommendations that went to government on how we can improve flood risk management in the future. A very comprehensive report. It was a great read. And to the credit of all the politicians, this isn't a political statement, but everyone involved, they took on board all of those comments, and the Flood and Water Management Act included every single one of those recommendations and came through in 2010. So this is when the lead local flood authorities were established, and the Environment Agency took control of the river catchments, and then the lead local flood authorities, and they look after the local flooding incidents. So there's a lot of good things that have come out of this as a consequence. If you move on to the next slide for us, Paul. And so sort of bringing us up to date, so looking at 2007, we had the Flood and Water Management Act 2010. That's come right up to date to 2021, so like 11 years later. We've got a Environment Agency DEFRA Innovation Fund, and there are 25 areas all over the country that have been identified, and they've just been notified of winning successful bids for a share of £150 million towards developing better flood responses, and an awful lot of those are using natural flood management techniques. So there's a lot more coming through the system as we speak. So it's a very timely time to be able to use this as a presentation on how you can go about and do this. And I think without further ado, I'll hand over to Paul to show us exactly how we can do that. So I hope that was of interest. And over to you, Paul.
Thanks very much, Pete. So on the presentation, by way of a quick addenda, I'll just do a very quick introduction to InfoWorks ICM for anyone who's not familiar with it. I'll look at some natural flood management applications, look at how you would build the catchment model, then go through optioneering, results and conclusion on this little example I've put together. So InfoWorks ICM, it's got a great track record. It's been in development for 40 years, growing out of HydroWorks, InfoWorks CS, which was the collection systems, and InfoWorks RS, which was the river systems. They were combined into InfoWorks ICM, which is integrated catchment modeling. So ICM is basically a way to offer one solution for the entire catchment model. So it's fully integrated river, urban drainage, overland flow modeling, so you can conduct all of the modeling in the same place with different scenarios, and you can use it to store all of your models in the same place. So then on to natural flood management. Pete's gone into this a little bit already in his introduction, but natural flood management is using techniques with natural processes to reduce the risk of flooding and coastal erosion. So examples might include slowing the flow, so restoring bends in rivers, installing leaky dams, planting more trees, or you could increase storage by restoring floodplains, creating storage, diverting flows to flood into areas that we prefer to flood rather than areas that we wouldn't like to flood. And again, increasing losses with infiltration. And as Pete said, that can be equated to large scale SUDS. So in today's example, I'm going to focus on installing leaky dams, planting trees, and diverting flows, and how we can use a model to quickly and easily optioneer flooding solutions and give proof of concept for outline designs. So next, Ben, if we can just go on to the next poll. So this poll is, have you used or considered modelling NFM measures as part of an integrated catchment flood plan? The percentage voted just creeping up there. So it's a fairly even split there between yes and no, and those who've considered natural flood model management, and those who've modelled them, and those who this is all new to. So that's quite good. So we can go back to the slides there. And I'll just give a quick overview on how you can get around to building the catchment model so you can start into natural flood management modeling. So in this case, the model history is started with an asset registry. So this is an area in the southwest of England, nice little coastal town. So we have the top of the drainage catchment here, all the properties. This is the urban drainage network, so these are the pipes coming down. And in the asset registry, they've also got incidents. So there's some flooding incidents around here and here, and they have operational incidents, such as some blockages, which you can see with these orange symbols here. And this all drains down to a treatment works, and then because this is a nice coastal town with a touristy beach in here, this all gets pumped off to a remote outfall. And from that asset registry, we can use that to create the hydraulic model. So within the InfoWorks environment, if that asset management system was in Info Asset Manager, that can just be a direct import in, a bit of data cleanup, and you can have the working network model. And then what you'd need to do is verify that against flow data to make sure that you're getting an accurate representation. So when they were doing the model verification, they noticed they had to add in some 2D areas around here, which is represented by this mesh, because they couldn't replicate the flooding incidents in this part of the network with just what was in the catchment. And there's quite a steep hill here, so they've modeled the 2D area to show the overland flow to represent this flooding. And similar in the town centre there, they couldn't quite match the flooding incidents, so they tried overland flow, still couldn't quite match it. Then they overlaid the asset registry on from Info Asset Manager, and so they had some blockages down here. And when they put the blockages in, that represented it. But what if there were also external inputs not in the model? So the runoff, the water course, and what if the other incidents weren't down to the operational aspects, but down to more external runoff, things like that. So the way to represent that is to turn it into a full river catchment model, as I've done here. So what I've done is I've downloaded the 1 meter LiDAR from the government website. I've imported the road and roof areas from the OS Zoom stack, and also the buildings. So I've imported those as mesh zones and porous polygons and other known features from the background mapping, such as woodland and green spaces, to give us a 2D mesh. I've used terrain sensitive meshing, which you can see here based on the ground model. This automatically adjusts the triangle size so you get more accurate meshing in the areas where the ground's changing a lot, and where the ground's fairly flat you get the larger triangles. And you can see that most evidently here where there's a culvert, and over the flat ground quite large triangles, and this is actually the water course coming through, quite well defined. And I've used quite small triangles for this demo purposes just to get a very refined mesh. I've used the normal condition on the boundary and raining directly onto the mesh. So in this case I've not applied an infiltration surface to the whole mesh, and I've got the roughness from an example from Chow, just for a global roughness of the catchment. So I did this model update in under an hour using existing available data. As such, it has some shortcomings, such as where I'm missing the top end of the catchment up here because I don't have the ground model, but that just misses off a tiny bit of this river upstream end, so I don't think it's going to be essential for this model. But I'm also missing the detail of the water course, particularly through the built-up area here. But because the ground model is so well refined, we can model the general 2D water course without using the 1D detail. So you've got the refined mesh, and that will give you the full 3D model, which you can apply rainfall to. And with time and budget, the model could easily be further refined to include all the relevant features, such as the water course, walls, hedgerows, and any true culverted or 1D modelling elements. But in about an hour, I think I've done a reasonably good job. So here's the model run. Initially I ran the baseline for a day to look at the full event and the drain down. This is looking at a 30-year, 60-minute storm, and you'll see the rainfall gradually falling on the upland areas, filling the rivers as it flows down the catchment and building up and eventually going out to sea. This full day simulation took about 4 hours just on my laptop, which isn't a particularly high spec. So I ran that overnight when my laptop was more or less dedicated to the task. After this, when I was playing around with the options, I ran 4 simulations in parallel at the same time, with a simulation time of 2 hours just to look at the peaks, and they took between 35 to 45 minutes to run in the background while I was working on other things. So just to zoom into the results in detail, you can see we've got 2 main catchments on the river. So we've got a smaller catchment to the north, this larger catchment coming in from the east. And then just in this area that's flooded here, you can see the roads are quite badly flooded. This was the area, if you remember from the verified model, where they added in the small area of 2D. So I've added in 3 results lines to show the flows from each of the upstream areas. So just to look at those results, you can see the majority of the flow is coming from the larger east catchment, as we'd expect, a bit from the north. And then that flooding that was being caused by just flow over the land from the hill, you can see that's peaking at about 0.4 meter cubed per second, and we're getting about 700 meters cubed coming through that results line. So then on our optioneering, one of the functions within ICM that makes it great for optioneering is scenario modeling. So in InfoWorks ICM, you can quickly and easily create alternate scenarios. So this video here will just show you some of the scenarios I've used. And using scenarios, we can simulate benefits and impacts of different options individually and when they're applied together. So for instance, if you're looking at removing a series of dams, you could look at a best sequence to remove those dams so that it's not going to cause flooding downstream. Another advantage of this is it lets you preserve the base model scenario, so you don't have to change your base model at all. You can keep that in place. And scenarios can also be used to model things like design horizon and range of efficacy. So for example, you could model a woodland at various stages of maturity to see what you could expect at different stages of the woods growing, and when you'd expect to see significant benefits. So whether the woodland was 1 year old, 5 years old, 25 years old. And then on to the examples I've picked. So the first one I wanted to look at was a leaking dam example. So for those not familiar with it, a leaky dam is like the picture Pete showed at the start. It's essentially a type of dam that at low flows, base flows, it will allow flows through normally, and then as the flows build up, it will hold back more and more as the dam compresses into itself. So first we use the map, the 3D ground model, and the 2D hydraulic model results to identify suitable locations. So in this case, I was looking for locations where if I put in a dam upstream, it's not going to cause any flooding to properties, and where we might have a significant impact on the flows. So this looked like a good area here. We've already got a bit of a flooded area where these two watercourses come together. There's no properties, no roads, nothing that's going to be impacted if we cause a bit of flooding in this area. So once we've identified a location, the best way to represent the leaky dam in a 2D model is to use a base linear structure to represent the weir and a sluice linear structure to represent the opening for the base flow. This video here is just me showing how to build that. So going into my scenario for the leaky dam, you can see there I've got the base linear structure. And it's quite a straightforward thing to set up. These are the properties you'd need to add. So in this case, I'm modeling it as a wall with an infinite crest height, just for design purposes. So once you've identified how high the water is likely to get behind that dam, you can then obviously refine the design a bit more. And then you could model it as a weir. If you choose weir, you can then model it as either broad-crested, thin plate, however you'd like. And you can set that to be either a height above the ground model or at a fixed level or irregular. In this case, just keeping things simple, using an infinite wall. And then for the sluice linear structure, in the middle of the base linear structure. And you can see here that we just need an opening height, the length of the sluice, and the start length, which is how far you want it along. So in this case, it's just covering the watercourse section of this dam. So I just measured along there, and I put it in as covering the watercourse in the middle, using the measuring tool. Everything else just leaving as the defaults. So once you've got that structure in, you can set it as to be fully free, orifice flows, however you want to control those flows through this sluice. And then you have the dam in. It is very straightforward. It's a case of putting in a couple of lines and then adjusting the parameters. The next example I was looking at was tree planting example. So I already have in some wooded areas in the model, which are these areas here, which I've brought in from the background mapping. So in this case, when I wanted to add in some, in this example, look at some new woodland, I've looked at adding upstream wooded areas to reduce flows. Another approach could be to add a natural buffer zone at the banks of the watercourse. Because I'm not using a defined watercourse model, I'm just using the 2D ground model to let the watercourse flow where it will. I've used this approach. The woodlands I've modelled as roughness zones based on roughness figures from Chow, and I've modelled them as mature woodland. I've also put in infiltration zones to represent how they would take in more water, and you'd expect more water to infiltrate from the woodland. There's less data available for infiltration based on woodland, so I've estimated it in this example based on some academic research papers I found online. But these could be corroborated on site with infiltration trial pits, for example. And I've placed those in the same way as I did with the leaky dam, in that I've looked at where the flows were coming off upstream, and I've planted trees accordingly. And here I've just planted one long line of trees to help protect this housing estate down here. And the final example I looked at was creating storage and diverting flows by putting in things like bunds. So where there's a need to directly protect properties, use earthwork bunds just by putting in a porous wall to divert flows to where they'll cause less harm or store water behind the bund. So then moving on to the results. So looking at the results line, so first looking at this northernmost catchment, and here I've put all those scenario results in at the same time. So this is looking at the baseline model. The red line is just with the leaky dam in, which is here. The green line is showing with just the added woodland. And then this brown line is the combined solution, so the leaky dam and the added woodland. So if you're looking at this northern catchment, as you'd expect, the leaky dam doesn't make any difference at all because it's all the way over here. Adding the woodland does make a fair reduction in the peak flow. This is just a modelling instability, so we can disregard that. But if we look at the peak flows, we can see that it's quite a big reduction by adding in this large area of woodland to take off those upland flows from up here. Moving on to the next set of results, here we've got a much more significant flow. It's a much larger catchment area. So we're looking at taking a lot less out just by this much smaller wooded area here and the leaky dam here. But by combining the solutions, we still managed to take a peak of 3 meters per second off the peak flow, and we're reducing the total volume by quite a significant amount, considering the size of that watercourse and the size of the flows we're getting down there. And just to zoom in on the area of the leaky dam, we can see here there's quite a significant difference between just the leaky dam on its own, so no additional infiltration or roughness behind here. And by adding that in combination with planting a new wooded area behind the dam, we're getting a big significant difference in the flows. So that's dropping from here all the way down to here. And the reason for that is because as we're holding flows back, we're also infiltrating them. The trees are taking up that water. So it's not just taking off the peak and then letting it flow down later. As you can see here with the leaky dam, it's slowing the flow, taking that peak off a bit, but the volume staying much the same as it's just going down later. By infiltrating it behind the dam, you're taking a lot of that flow out from downstream. And then finally looking at this housing estate. So obviously the leaky dam doesn't make any difference at all, but by adding the woodland in, we're making a massive difference. We're chopping in half the peak flows and the volumes. So your next scenario may be looking at, this is an existing woodland here, this is the new one I proposed. So you could quickly do a second scenario of looking at, do we need woodland along the whole line, or could we just cut out where we've got these obvious watercourses coming down the hill and do a much smaller area of woodland to save some budget? Well, that's the sort of things you can look at there. And then the final option we discussed was putting in some bunding. I'm just going to show this with a video. So this is the bund I've added. This is the line of the watercourse. We've got two natural sand dunes here, which the watercourse runs in between, down the beach and out to sea. And as this plays through, you'll see that the watercourse fills up. And the problem we have with this solution is that we're getting overland flow coming down from this direction and building up behind the bund. So it's doing its intended job. It's stopping the flooding from the watercourse from impacting on this. This is a caravan park. So this is being held behind the bund. It's not impacting on the caravan park, but the overland flow is building up against the bund. So it may not be an ideal solution in this situation. But that said, if we look at the results, if I can bring my video control up. That said, I can't get the graph up at the moment, as is the way with live videos. But what actually happened is that the flooding behind the bund, because it was only the overland flow, actually reduced down from 650 mil to about 200 mil. And that might be acceptable. It's certainly a great improvement, but I would imagine the owner of the caravan park wouldn't be happy if you'd put in this big bit of earthworks and it hadn't completely solved the flooding. So you could look at that in more detail with further elements of the model. So in conclusion, we can use ICM to quickly and easily model a variety of natural flood management measures. I've demonstrated some today. There's obviously a lot more. You can use it to model things like fish passes, all sorts of natural upstream catchment measures. You can use scenarios to optioneer solutions, provide proof of concept, outline design and test detailed designs individually and in series. And you can use that for a design horizon scenario as well. So what will this woodland be like in 1 year's time, 5 years' time, 20 years' time? And finally, natural flood management measures tend to work best in concert as part of an integrated catchment plan. And this can best be represented by an integrated catchment model. So by including the upstream catchment areas and the river and seeing how that's going to impact on the flooding down in the built environment, you can include the drainage area and see what the impact that has, and you can time naturally when the peak of the river is going to be and when the peak of the drainage system is going to be, and see whether they're going to coincide. Does the peak of your river flooding hit the same time as the peak of your drainage system flooding, for instance? And that'll take us nicely into our final poll. So, are you more likely to consider natural flood modelling and natural flood management modelling?
That was really great, Paul.
Sorry, just taking the opportunity of the poll just to have a quick drink.
Don't blame you. No, it was really, really fascinating, and I just love like seeing those results coming out. You know, with the different options, the individual. You can see the benefits from the individual elements, but the combination of all as well is really powerful. I feel so. That's
yeah.
Great.
I think the great thing to note about this is, as I said at the start, this was just adopting an existing model using available data. In about an hour, I created that full river catchment model, and that can be used to give you a quick proof of concept. If you do decide it's worthwhile doing, you can then go and get the additional data to refine the model more and use it to put that case forward even better. But for an hour with existing data, it gives you that great first step.
It does. It really does. Yeah. Well, I don't think I've ever seen such a comprehensive feedback after a presentation. That says it all, doesn't it? It's great. I mean, there have been a lot of DEFRA pilot studies. As I mentioned, the EA DEFRA Innovation Fund in the 25 different areas. Some of them are coastal, some of them are inland, and a lot of them are looking at natural flood management techniques as well. So it's really, really timely and really, really helpful. And thanks for that excellent presentation and the feedback.
And it's all about that horrible phrase that got used too much in the pandemic last year, but flattening the peak. So if you can take a bit of the peak off upstream, then even if you do need to do additional measures downstream in the catchment as well, such as old-fashioned traditional building a tank, you might be able to get away with a much smaller tank for storage. Your SUDS measures may not need to be as extensive. So it's all about, as you said, a patchwork and a mosaic of putting lots of smaller elements together, so you don't need that one big, massive, old-fashioned storm tank.
And again, I pick up on a point that you made just to really emphasize the importance of it in case it got kind of missed whilst the poll was going on. But the point that you made about, you know, how the response to the pipe network is so radically different to the response to the natural water channels, the rivers, etc. So
it can be, yeah.
And it's those kind of combined probability to have that integrated model to run a whole series of different return periods and storm durations, and then identify what the critical storm durations are for the rivers, what they are for the pipes in different parts of the network will vary quite radically, and then put in the appropriate measures in the appropriate places. It just helps you to refine and help with that thought process straight away. So leading into the questions, you were mentioning about the data set took about an hour, etc. So Chinedu is asking, are these data sets open source and are they publicly available? How can we get our hands on them, kind of thing? Where would you steer people towards?
That depends on where you are. I'm unfamiliar, obviously, with the UK data set. So in the UK, DEFRA have a website where you can freely download LiDAR data over most of the United Kingdom, well, most of England, Wales and Scotland have a separate website where they do it. And that's generally available as DEMs and DTMs of different resolutions depending on where it is. So city centres tend to have quite well-refined resolutions, and known problem areas tend to have quite well-defined resolutions. For things like the background mapping, I've got access to the OS OpenZoom stack, which I use for this example. There's lots of different places you can get background mapping from and GIS from. For GIS software, Mapinfo and Arc will work directly within ICM. There's also QGIS, is a free GIS software where you can do a lot of data manipulation in there.
Mm.
So yeah, it's hard to say where data is available from without knowing where you are. But yeah, in my case, I've just downloaded it.
Yeah, maybe we can produce a little bit of a list with some links so people can kind of access that and have a look after the presentation. Leads in nicely to a point from Hossein, with regard to the model properties. So how did you model the actual properties? Mesh or protrusions is the question there, Paul.
By properties, I'm assuming you mean the buildings in this.
Yeah, that's what I'm reading.
Porous polygons in this model.
Mm-hmm.
So that's a feature within ICM whereby you can mold, similar to the way the porous walls I showed for the bunding work, in that you can model it with a height and you can set various functions within that porous polygon. So just by using the boundaries from the OS data, I've brought that in as porous polygons. I've set it to a height of a standard building height. I think I use 6 meters. If I was interested in looking at the property flooding for this, I could then set those properties, those porous polygons, to become porous under certain conditions. Mm-hmm. So for instance, if the depth of water reached above 300 mil, which would be a fairly standard threshold height or air brick height, you could set that to then enter the properties so that the porosity would go from impervious to pervious and the water would be able to flow through. You could also model them as mesh zones and just raise the mesh, so that would be a way to also show them on the 3D map. So I hope that answers the question, but these are all functions included in the ICM software to just do it automatically.
And you just triggered me on that one when you mentioned, like the thresholds, etc. So you could have the sort of door threshold heights, if you like, set for the properties, and then when they breach, then that becomes kind of flooded. That would show as a flooded polygon on the plan, and then we could link that to the multicolored handbook, couldn't we?
You can. So it's a way to differentiate between internal and external flooding. There is another module in ICM Riskmaster which links directly to the multicolored handbook, so you could use that for economic flooding and economic flood risk.
So extra sort of benefit there. Great question from Michael. You use peer review papers like Chow you use peer reviewed papers to estimate the infiltration values for the mature woodland. Are there any specific papers you used, or any that you would particularly recommend?
I just did a Google search, and because this wasn't for a real life project, what I did was I found the first 5 papers I found. I looked within most recent years, so within the last 5 to 10 years, and the first 5 papers I found, I used them. They were all fairly consistent. But I haven't done any direct research myself to be able to validate them. As I say, that with roughness, there's a lot of published material. Chow is an almost universally accepted table for roughnesses now. That's been around since the 50s, I believe. Chow was first published.
Even I recognise Chow when you mention it.
Yeah. But with the infiltration, as I say, that there's a lot less that I could find, at least, accepted literature. So in this case, as I say, I just Google searched, looked for it, but I wouldn't have enough to say, look in this textbook and it will give you a figure. As I say, you could use trail pits on site to test infiltration of the open ground. It's then using a figure for wooded areas.
Yeah, exactly.
I don't have those
100%.
papers I used to hand. They're on my computer somewhere, but I don't have that hand to be able to point you in any directions other than just say Google it. There is a growing amount of research out there. This is something people are looking into, but I don't have that in hand. Sorry.
Yeah, and I definitely back you up and say, look, if you are going to use infiltration in the ground, you would need to do some percolation tests on site.
Yeah.
Because the growing conditions can vary so radically, so that we need to do some percolation tests, BRE Digest 365 kind of percolation type test.
Yeah.
Right.
It's great for the existing situation. It's just then estimating what would happen when you planted a woodland and what would happen when that woodland's 1 year old, 5 year old, 10 year old, fully mature.
Yeah. You mentioned validation, Paul. Have you validated the performance of the model for such features as leaky dams and trees, etc.?
I haven't for this one. As I say, this was thrown together in about an hour from the existing model, and it's not for a live project, so it hasn't been validated, but that could be done.
Yeah, and I mean, we will be involved in a lot of such projects, I would say, moving forward. So we'll have lots of good kind of case studies that we can share with people as well. So thanks for that, Johannes.
It has been done. I haven't done it.
Yeah. Michael's asking, did the NFM options still have much of an impact on the higher return periods? You mentioned sort of 30-year, 60-minute, etc. Have you tested it for the higher return periods, 100-year, and adding in climate change and what have you?
I haven't as yet looked at high. I've looked at the 30-year and the 5-year. I did run a 100-year, but I haven't got the results saved, so I can't look at it. But in this case, you would have to look at your designs. Because I was just doing this as an outline design, as a proof of concept, all of my dams and walls and things are of an infinite height. So it would still have an impact. But what you'd have to do when you consider the design, obviously you can't make an earthworks bund of infinite height, so you would design it to a certain threshold. So if I was progressing this model, I might run a 100-year plus climate change event through it, see how high I needed that weir to be, see how high I needed that earthwork bund to be, and design them to that height, then put them in as a broad-crested weir of that height. Then I could run a larger event through and see what the failure mode would be. So that would then show you what was overtopping that weir in a 150-year event, a 200-year event. Personally, I wouldn't go much higher than that because leaky dam structure wouldn't survive, in my opinion, a 1,000-year event anyway.
It's a good point. Yeah, it's likely. Well, it depends on the flow, etc. And again, you don't know that until you create the model and run the analysis. Kind of what we're dealing with, whether it be coming flow down the channel or flow off the hillside, and to see literally the flows and the volumes that we're talking about, you can then start making engineering judgments.
And in the same way as the porous polygons, you can model those to fail under certain conditions. So if your designer told you that the earthwork bund would only survive a depth of water up to 0.8 of a meter, you can program that into the model and it will just fail at the point where the model says it's going to fail. So if along the bund the depth of water is only 200 mil, and then at one point it rises up to 800 mil because there's a dip or a dip in the ground or what have you, then it will just fail at that point and you'll get the catastrophic flooding failure model.
Yeah, I'm thinking that with flood barriers and front gates and front doors and things like that, you could get to a point where it reaches sort of a meter or two height and then all of a sudden, the thing will fail. More questions coming in. Is there any technical guidance for modeling NFM in ICM?
At the moment, there's not much more than what I've just done, but all of the features I've described are within the help file. So if you look in the help in ICM, it will show you how to use all of these features, such as the the porous walls, the base linear structures, everything like that.
Great.
This presentation was more to show that they can be used in that way, because I think a lot of people use ICM just for the traditional drainage structures. So they use it within the urban drainage catchment and maybe haven't considered the upstream stuff. So all of the things I've shown today are in the help file showing you how to use them. And this was just giving some ideas of how else you could use them.
Yeah. Roger's asking, can you include storage being activated at a range of events?
I'm not sure I understand the question, but you could include...
Constrained to a range of events. And maybe we put in sort of offline storage, and so they would trigger for particular events, maybe, is what I'm kind of interpreting that as.
Yeah, I'm sorry. If you could type in a bit more of a clarification on your question, Roger, we can get back to it. But yeah, you can use things like real-time control to activate or unactivate storage. You could have weighs at different levels, for instance, so that they go at different events. You could use initial conditions to show how a storage was already full at the beginning of event and see how that would impact. Or just use an extended rainfall period where you did have some back-to-back storms in it. So I think I've covered a lot of the possibilities there, but if you could just clarify.
Yeah. And I think you've answered Lydia's question as well about modelling.
I think we just missed one. Did we miss Michael's?
Oh, sorry. Yeah, the tree planting. How does the tree planting create infiltration for surface water? Sort of sitting at the base of the trees or the trunks, kind of question mark?
There's two ways from the research I've done. So there's a small effect from less water actually hitting the ground at the beginning of the storm, because it's hitting the leaves, and obviously there's a small degree of that water doesn't all get to the ground at the same time, so it slows down the flow in that way. Then there is the impact of, if the water is sitting there, the trees will soak it up, and because of the tree roots, etc., you get more infiltration within the soil.
Yeah,
I'm not a ground engineer to be able to use the technical term, but essentially there's more granularity, more runoff through the soil.
Yeah, and it's going to depend on the subsoil there as well, and again back to doing the infiltration tests in the first place as well.
Yeah,
as well as adding in the trees subsequently, kind of thing. Lydia's asking, that's about the stages with the woodland, which you covered, so you can do various stages of the woodland.
So the obvious one with the woodland, if I stick to chow, you've got different levels of ground coverage for roughness in chow, which is all slowing down the flow. For the infiltration, again, as I've said again and again, it's using what research is available to do the estimates of how much extra water input take up you'd expect from a young woodland, a mature woodland, etc.
Great. My questions have just done a little bit of a resort on me, so I'm going to have to, oh gosh, it's changed the sequence of them, but that's okay. From Rory, are local authorities hesitant to implement NFM measures such as leaky dams due to some required monitoring and maintenance? No, that's a good point, Rory.
I think you're better placed to answer that than me, Pete. You deal with them more.
Yeah, I mean it depends. Yeah, who's the owner? This is one of my kind of pet things actually, Rory, because what I'm feeling is, whether it be NFM or whether it be SUDS, these will like materially impact flooding within an area. So the lead local flood authorities should definitely be keeping a register of such things, but they may not be the owners of them. But they need to know where they are, what they are, who owns them, and the condition. Now they should be, and if there are people from the local authorities on the line, I mean, correct me if I'm wrong, but you should be getting some funding because of your LLFA role to deliver that. but I'm imagining that you're not getting that funding directly coming through. So it's a very, very good point. I've not heard of that myself. I've heard no reluctance. If anything, the people that I've been involved with recently are very keen on the whole idea because of the multiple benefits, not just the flooding, but the multiple benefits that are coming with biodiversity and improved ecosystems. So not heard that, but do correct me if I'm wrong and post in the question box if you're from a local authority and we can pass that on. Can Peter's model be created with micro-drainage or just InfoWorks? Well, I mean, I'd answer that. I wouldn't attempt this in micro-drainage. We need to have a fully integrated catchment model with everything. Would you agree, Paul?
Yeah, this level of complexity you couldn't do in micro-drainage. It wouldn't be able to cope with it.
Yeah, I think the complexity, the nuances, you know, with those weirs and what have you, we could put in real-time controls, but it's not designed for that purpose. It's a design tool. The other thing I'm thinking is Paul mentioned some of the run times of like 4 hours. Now, the larger the model and the more complex the situation, then the longer the run times will be. And with InfoWorks ICM, you can harvest out onto your IT network to all the kind of latent PCs, or if you had a supercomputer somewhere, you could hive out that simulation or some simulations to different PCs across the network and speed up the whole process for you. Roger's asking, can you include storage being activated over? Sorry, that was one I've already asked. This is my rejiggled list. Lee is asking, could you please advise what's the difference between using info drainage and ICM on NFM modeling? It's a little bit like a micro drainage ICM. Info drainage I would usually on a new design, a brand new development, a brand new design. But if you're looking at putting in natural flood management techniques on an existing catchment, then I would use InfoWorks ICM for integrated catchment modeling. So, and you can get variant sizes. If it's not the biggest of models even within InfoWorks that you would require, you have different sizes of packages. So you could start off with like 100 nodes and things like that.
If you think of it as micro drainage and info drainage, they're design tools that you can use to do a little bit of analysis. ICM is an analysis tool that you can use to do your initial and outline designs. Yeah.
I'll just ask one more question because I'm going to have to scoot at 2, and I want to hand over to Ben. But here's a quick one from Jess. Does the rainfall runoff FEH info, or basically is the rainfall runoff info from FEH or RefH2 or a combination of both?
In this case, it's FEH, but ICM will use either of those or a big long list of other types of rainfall.
Or real-time data, etc.
Or you can use historic data, you can use radar data, live data, what have you. So yes is the short answer.
Super. Thanks so much for all the questions, folks. For those that we didn't get chance to answer, we'll answer them and send out as an FAQ. But with that, I'll hand over back to yourself, Ben. And thanks again, Paul. That was brilliant. Really interesting and engaging, and loved it. Lots of great content there. Thank you very much.
Yeah, brilliant. Many thanks to Paul and our resident host, Peter Coombs, for the webinar today. Any questions we did not have time to cover, we will come back to you with an answer, as Pete said. I'll be updating you with a recording of this webinar next week, along with our fresh upcoming webinars that I hope you'll be able to join us for. Please remember to complete the short survey that follows this webinar. In return, you'll receive an attendance certificate to use for CPD. These certificates will be sent out from GoToWebinar in 5 days' time. As always, don't forget to check out our upcoming training courses. You can visit our website for more details about them. And finally, a big thank you for joining us today. Have a great day, everyone.